Welcome to Cosmos and Dreams. Tonight, we explore a signal that crossed the universe, pulsed with impossible precision, and vanished, leaving scientists with a pattern they cannot explain and a silence even deeper than space itself. If the universe is your kind of bedtime story, subscribe before you drift off. Now get comfortable, close your eyes, and let science carry you to sleep. Opening meditation. There is a sound you have never heard. It came from somewhere in the universe, from a direction we can roughly point to, from a distance we can only estimate in numbers so large they lose their meaning. It arrived at a radio telescope in the middle of an Ohio summer, etched itself into a paper printout, and then vanished. It has never come back. For a single 72-second window, the universe seemed to say something. And then it went quiet again, as if it had thought better of it. As if it had changed its mind. Tonight, we are going to follow that signal. Gently. Slowly. The way you trace a river upstream to find where it began. We will sit with the scientists who spent their lives listening to the sky, who built enormous dishes and pointed them at the stars not because they expected an answer, but because they believed the question was worth asking. You don't need to stay awake for this. In fact, the most beautiful parts of this story live best in the soft edges of consciousness, in that warm space between waking and dreaming. Let your breath slow down. Let your body settle into whatever surface holds you now. The universe is approximately 13.8 billion years old. In all that time, in all that silence, something happened on August the 15th, 1977. Something that the astronomer who found it circled in red pen and labeled with a single word. That word was, wow. And with that quiet word, everything changed. And nothing was ever the same. And yet, somehow, nothing was ever confirmed. Let that settle over you now, like a blanket being drawn gently up around your shoulders. Something happened. We just don't know what. Part 1: The Art of Listening to the Sky. What would it mean to actually hear the universe? This is not as strange an idea as it might first appear. The universe is filled with radiation, electromagnetic energy of every kind, rippling outward from stars and galaxies, from dying suns and spinning pulsars, from the thin background glow left over from the very beginning of time. Most of this radiation is invisible to human eyes. But it is not silent to our instruments. Radio waves are a form of electromagnetic radiation, just like visible light, but with much longer wavelengths. They can travel enormous distances through space. They pass through clouds of dust and gas that would block ordinary light. They can carry information across the cosmos with remarkable fidelity, arriving at our planet after journeys of thousands or millions of years, still carrying the signature of whatever produced them. The idea that we might detect radio signals from space, and that some of those signals might come from intelligent sources, began to take serious scientific shape in the middle of the 20th century. It was not a fringe idea. It was not the domain of enthusiasts alone. It attracted some of the finest minds in physics and astronomy, people who understood that if the universe was vast enough, and old enough, and if life had arisen here on this small blue world, then the same chemistry and the same physics might have produced life elsewhere. The logic was simple and devastating in its implications. The universe contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. Many of those stars have planets. The chemical building blocks of life, carbon, hydrogen, oxygen, nitrogen, are among the most abundant elements in the cosmos. If life arose here, under these conditions, why not elsewhere? And if intelligent life arose here, why not elsewhere too? This was the reasoning that drew serious scientists to the problem. Not the hope of little green men, not the romance of science fiction, but the cold arithmetic of probability applied to the largest numbers in existence. In 1959, two physicists named Giuseppe Cocconi and Philip Morrison published a paper in the journal Nature that changed the direction of modern astronomy. Their paper asked a precise and elegant question: if an extraterrestrial civilization wanted to communicate with us, how might they do it? And their answer was equally precise. Radio waves, they argued, were the most logical medium. They travel at the speed of light. They cost relatively little energy to produce. They pass easily through interstellar space. And there was a particular frequency that Cocconi and Morrison found especially compelling. Hydrogen, the most abundant element in the universe, emits a characteristic radio signal at a frequency of approximately 1420 MHz, corresponding to a wavelength of about 21 centimeters. Any civilization with sufficient technology to build a radio telescope would know about this frequency. It was, in a sense, a universal landmark. A cosmic signpost. A place in the radio spectrum that any intelligent observer would recognize. The two physicists argued that if you wanted to be found, you might broadcast near this frequency. And if you were searching, this frequency was a logical place to begin. Their paper ended with a sentence that has echoed through the decades since. The probability of success is difficult to estimate, they wrote, but if we never search, the chance of success is zero. It was a sentence that moved people. It inspired action. Within a year, an astronomer named Frank Drake had pointed a radio telescope in Green Bank, West Virginia, at two nearby sun-like stars and listened for signals. He called it Project Ozma, after the Queen of Frank Baum's imaginary land of Oz, a distant, mysterious, difficult-to-reach place. Drake heard nothing extraordinary from those stars. But he had started something. He had begun the era of listening. In the years that followed, the search expanded. Radio telescopes around the world were pointed at stars and galaxies. Researchers developed better equipment, more sensitive receivers, wider ranges of frequencies to scan. The field acquired a name, the Search for Extraterrestrial Intelligence, or SETI. It attracted funding, then lost funding, then attracted it again. It attracted ridicule and wonder in roughly equal measure. But through all of it, someone was always listening. Someone always had their ear pressed to the great silence of space, waiting for a sound that didn't belong there. Waiting for something that should not exist. And in one particular place, at one particular institution, a group of scientists had built something remarkable. Something large enough and sensitive enough that if a signal was out there to be found, they might find it. They called it Big Ear. It was not, as radio telescopes go, the most glamorous instrument in the world. It was not the enormous dish in Arecibo, Puerto Rico, carved into a natural valley in the jungle. It was not the sprawling array at Socorro in New Mexico. But Big Ear was unique in its own way, and it was pointed at the sky with the same patient, unhurried dedication that defines the best scientific listening. Big Ear was a flat, sprawling structure on the campus of Ohio State University, covering an area roughly the size of 3 football fields. It consisted of a flat reflective surface on the ground, flanked by 2 large flat panels that could be tilted at different angles to capture radio waves from different parts of the sky. It couldn't be steered in the way a conventional dish telescope could. Instead, it relied on the rotation of the Earth itself to slowly sweep across the sky, like a searchlight panning across a dark ocean. Every day, as Earth turned on its axis, Big Ear would scan a different strip of sky. Whatever radio sources happened to pass through its field of view, it would record. Its reach was not infinite, but it was impressive. And it was patient in the way that only machines can be, recording day to day after day, month after month, year after year, with no need for sleep, no need for rest, no wavering of attention. But the scientists were patient. They were looking for something specific, a narrowband signal, a signal confined to a very small range of frequencies, the kind of signal that a natural astrophysical source generally does not produce, but that a radio transmitter designed by an intelligent mind very specifically would. And so they listened. And the data piled up. And the years passed quietly. Until one August, on a printed computer readout, something arrived that had been waiting for them in the data for several days, unnoticed, until a volunteer astronomer sat down to review the numbers. And everything changed. Or perhaps nothing did. That is the strange beauty of this story. It holds both possibilities at once, like a coin balanced on its edge, and it has never fallen. Part 2, The Man Who Heard It First. What does it feel like to find something you have spent years looking for, and then not know if it's real? His name was Jerry Emmon. He was an astronomer and a computer programmer, a quiet and methodical man who had been working as a volunteer with the Ohio SETI program since its early days. He was not a celebrity scientist. He was not hunting for fame. He was the kind of person who shows up because the work matters, because the question is worth asking, because someone has to sit down and look at the data. In August of 1977, Emmon sat down with a stack of computer printouts from Big Ear's recent observations. The data was displayed in a format that required human eyes to interpret, columns of numbers and letters representing the strength of radio signals detected at different frequencies during the telescope's slow scan of the sky. The numbers were encoded alphanumerically, low signals were represented by the number 1, slightly stronger ones by 2, 3, 4, and so on, and once the signals passed a certain strength, they were represented by letters. A was 10, B was 11, C was 12, and so on. Most of the printout was filled with 1s and 2s. Background noise. The ordinary murmur of the universe going about its business. This was what Emmon expected to see, because this was almost always what there was to see. But as he worked through the data for August 15, 1977, he came across something that made him stop. There in the columns was a sequence of characters, 6EQUJ5. Take a moment to let those characters settle in your mind. 6. EQUJ. 5. In the alphanumeric encoding the telescope used, this sequence represented a signal that rose from moderate strength to extraordinary strength and then fell away again, tracing the precise bell curve shape that Big Ear would produce as it swept past a point source, a source of radio emission at a fixed point in the sky. The signal peaked at strength U, which in the coding system meant a value of approximately 30. This was more than 30 times stronger than the background noise, far above anything that could be explained by ordinary cosmic radiation. The signal appeared at a frequency very close to the hydrogen line. The most important frequency in the universe, the one that Cocconi and Morrison had pointed to 18 years earlier as the most logical place for an intelligent civilization to broadcast. Emin circled the sequence in red ink. And in the margin of the printout, he wrote a single word. Wow. That word, that single, understated, profoundly human exclamation, would become one of the most famous annotations in the history of science. The signal itself would forever after be known as the wow signal. Now, it is worth pausing here to understand what Emin did and did not do in that moment. He did not call a press conference. He did not rush to publish a paper claiming that humanity had made first contact with an alien civilization. He was a scientist, and scientists are trained to be skeptical of their own excitement. He knew that the data was striking. He knew that what he was looking at was unusual, perhaps unprecedented. But unusual is not the same as explained. Striking is not the same as understood. What Emin had found was a signal. A real, measurable radio signal. The question that would define the next several decades of his professional life and the lives of many others, was what that signal was. Where it came from. What produced it. And here is where the story becomes genuinely strange. Because when scientists went back to look for the signal again, when they pointed Big Ear at the same patch of sky, at the same frequency, listening carefully, the signal was not there. It had been there once. 72 seconds. A single sweep of the telescope's beam across one point in the sky. And then it was gone, and it never came back. In the weeks after Emin's discovery, the Ohio SETI team devoted significant time to re-observing the region of sky from which the signal had apparently come. They pointed Big Ear at that patch of sky again and again, using every available resource. Other researchers heard about the signal and aimed their own instruments at the same location. The Great Radio Telescope at Arecibo, one of the most powerful listening devices ever built, was trained on the coordinates. Nothing. Jerry Emin spent years thinking about what he had found. He published analyses. He listed the possible explanations. He was careful and honest in his uncertainty. In interviews decades later, he would reflect on that moment of discovery with the measured calm of a man who has learned to hold open questions with grace. He had written the word wow. He had meant it. But he had never claimed certainty about what it meant. And that, perhaps, is the most scientifically admirable thing about the story. The honesty of it. The willingness to say, something happened here. I do not know what it was. I am still listening. The printout itself became a historical artifact. The original computer paper, with Emin's red ink circle and his handwritten annotation, has been preserved and exhibited. It is a small, unassuming piece of paper for something that may be one of the most significant documents in human history. Or it may be a curio, a misidentified artifact of some mundane and earthly source of interference. The honest answer is that we do not know. After nearly 50 years, the wow signal remains unexplained. It remains the single most compelling candidate for a detected signal of extraterrestrial origin that science has ever recorded. And it has never repeated. Which brings us to a deeper question, one that will occupy us for much of this journey. What would we need to find, to be certain? What does proof look like when the evidence arrives only once? Part 3, Big Ear, a portrait of the telescope that changed everything. How do you build a machine to listen to the universe? To understand the wow signal, we must understand the instrument that detected it. Because the characteristics of the telescope, its shape, its sensitivity, its limitations, are essential to interpreting what was found. Every scientific instrument has a personality, a set of strengths and blind spots, and Big Ear was no different. The telescope had its origins in a vision held by John Krause, an electrical engineer and radio astronomer at Ohio State University. Krause was a remarkable figure in the history of radio astronomy, a man who combined practical engineering ingenuity with a deep scientific imagination. He had spent years studying radio waves, from their propagation through the atmosphere to their emission by cosmic sources, and he had developed ideas about telescope design that were unconventional but effective. The telescope he designed for Ohio State was what engineers call a transit telescope, or a meridian telescope. It could not swivel and point at specific objects the way a steerable dish can. Instead, it was fixed in place, and it relied on Earth's rotation to bring different parts of the sky into view. As the planet turned on its axis, the telescope's fixed field of view swept across a strip of sky, like a fixed camera watching a parade pass by. Each point on the sky was in view for only a limited time. That limited time was approximately 72 seconds. 72 seconds. The same duration as the wow signal. This is not a coincidence. It is, in fact, one of the most important pieces of evidence about the signal's nature. A signal from a fixed point in space, a point source that does not move relative to the stars, would be in view of Big Ear's beam for exactly 72 seconds as the Earth turned. The wow signal lasted exactly that long. It was not cut off abruptly. It did not fizzle out prematurely. It rose, peaked, and fell in the precise bell-curve profile that you would expect from a point source passing through the telescope's field of view. This is significant. It tells us that whatever produced the signal, it was not moving relative to the stars. It was not a terrestrial radio transmitter, which would have moved with the Earth. It was not a satellite in orbit, which would have swept past much more quickly. It was not an aircraft. The duration and shape of the signal were consistent with a source at an astronomical distance, fixed against the background of stars. Now, let me describe Big Ear more fully, because it was a remarkable structure in its own right. The telescope consisted of three main components. There was a large flat ground plane, a reflective surface laid out horizontally, roughly 90 meters wide and about 500 meters long. At one end of this ground plane stood the fixed flat reflector, a large tilted panel about 100 meters wide and 30 meters tall, angled to direct incoming radio waves toward the center of the telescope. At the other end stood the tiltable flat reflector, a similar panel that could be adjusted to select different declinations, different strips of the sky at different angular elevations. At the focal point of this arrangement sat the feed horn, the actual radio receiver, a metal structure that collected the focused radio waves and converted them to electrical signals, which were then amplified, processed by a computer, and printed out on paper tape in those columns of numbers and letters. The whole structure was enormous. Walking across the ground plane would have taken several minutes. It sat in a field on the outskirts of Columbus, somewhat unremarkable from a distance, not obviously impressive in the way that the great dish telescopes are, but immensely sensitive to the frequencies it was designed to detect. The telescope also had two separate feed horns, positioned to observe slightly different parts of the sky, what engineers call the positive feed horn and the negative feed horn. A genuine signal from a point in space would appear first in one feed horn and then, about 3 minutes later, as the Earth's rotation continued, in the other. The wow signal appeared in one feed horn only. This is one of the puzzling aspects of the signal. If it was truly from a fixed point in space, both feed horns should have detected it, 3 minutes apart. The fact that only one horn registered the signal has been cited by some researchers as a possible argument against its astronomical origin. Perhaps it was a local source of interference that happened to fall within the first horn's field of view but not the second's. Or perhaps the signal was simply not repeating, perhaps it was a single, non-repeating pulse that happened to occur during the observation of the first horn only. Scientists have argued both sides of this question extensively. The honest answer is that the missing detection in the second feed horn is an unexplained anomaly that neither confirms nor rules out any of the leading hypotheses. It is one of many aspects of the wow signal that keeps it tantalizingly undecided. What is not in doubt is that Big Ear was one of the finest instruments of its kind, operated by a team of dedicated scientists who knew what they were looking for and understood the data they were collecting. The Ohio SETI program was not amateur work. It was not fringe science. It was a serious, methodical, long-running scientific survey, and the signal it detected deserves to be considered in that light. Over the 22 years that Big Ear operated, it recorded billions of data points. Of all those data points, the wow signal stands alone. Nothing else in the entire history of the survey came close to it in terms of its combination of strength, narrowband nature, duration, and frequency. It was the single brightest star in a universe of noise, a spike of intensity that leapt off the printout and demanded attention. And then it was gone. The telescope kept listening. The data kept coming. Years passed. Big Ear was eventually demolished in 1997 to make way for a golf course, a fact that many in the scientific community found, to put it diplomatically, rather disappointing. But by then, its work had been done, its data preserved, its most remarkable discovery already enshrined in the history of the search. The wow signal survived its telescope. It outlasted the instrument that found it. It persists in the literature, in the data, in the minds of scientists and curious people around the world, as a question that was asked and never answered. Part 4. The hydrogen line, the universe's own frequency. Why would the most abundant element in the universe become the key to a cosmic mystery? To understand why the wow signal's frequency is so significant, we need to spend a little time with hydrogen. This is not a diversion. This is the heart of the story, because the frequency at which the signal was detected is not incidental to what it might mean, it is arguably the most important fact about it. Hydrogen is, by a very large margin, the most common element in the universe. It makes up approximately 73% of all ordinary matter in the cosmos, all the matter that is not dark matter, not dark energy, not the mysterious substances that dominate the universe's composition but remain largely invisible to us. Stars are made primarily of hydrogen. Vast clouds of hydrogen gas float between the stars, the raw material from which future generations of stars will be born. Hydrogen is in the water that fills the oceans of our world and the atmospheres of gas giants. Hydrogen is everywhere. In its simplest form, a hydrogen atom consists of a single proton orbited by a single electron. This elementary structure has a property that proves enormously useful to radio astronomers. The electron and the proton each behave like tiny magnets, and they can be oriented in two ways relative to each other, their magnetic fields aligned in the same direction, or aligned in opposite directions. When a hydrogen atom transitions from the aligned state to the anti-aligned state, it releases a tiny packet of electromagnetic radiation, a photon, at a very specific frequency. That frequency is 1420.4 MHz. The corresponding wavelength is approximately 21 centimeters. This transition happens spontaneously, without any external trigger, and because there is so much hydrogen in the universe, the cumulative effect is a persistent, detectable signal at this frequency that permeates the entire cosmos. Radio astronomers discovered this emission in 1951, following a prediction by the Dutch astronomer Hendrik van de Hulst, who in 1944 had calculated that such a transition should be detectable. The discovery opened up an entirely new branch of astronomy, allowing scientists to map the distribution of hydrogen throughout the Milky Way and beyond, tracing the arms of our galaxy through the fog of dust and gas that would otherwise conceal them. But the significance of the hydrogen line for SETI goes beyond its practical usefulness. Cocconi and Morrison, in their 1959 paper, pointed to the hydrogen frequency as a natural choice for an intelligent civilization that wanted to be found. Any technological species capable of building a radio telescope would be aware of this frequency. It is, in a sense, the most recognizable landmark in the radio spectrum, the one frequency that any civilization, anywhere in the universe, with any history and any culture, would know about, because it is written into the physics of the simplest atom. If you wanted to send a message to unknown recipients whose language and culture and history you could not possibly know, you would look for common ground. And the most fundamental common ground in the universe is physics. The laws of physics are the same everywhere. The hydrogen atom behaves the same way on the far side of the Milky Way as it does in a laboratory in Ohio. And so the hydrogen frequency is a kind of universal language, a frequency that any intelligent observer would recognize regardless of where they came from or what they looked like or what concepts they had developed in their particular corner of space. This reasoning was formalized further by Frank Drake and others, who developed the concept of the cosmic watering hole, a range of frequencies between the hydrogen line at 1420 MHz and the hydroxyl radical emission at approximately 1700 MHz. Together, hydrogen and hydroxyl form water, H2O, the molecule most associated with life as we know it. The frequency range between these two landmarks was called the watering hole because, metaphorically, it was the place in the radio spectrum where different species might gather, where the signals of the universe's living things might converge. The WOW signal was detected very close to the hydrogen line, within the watering hole. This is one of the aspects of the signal that makes it particularly tantalizing. It was not found at some random frequency. It was found precisely where the theoretical predictions said you would most likely find a deliberate broadcast from an intelligent source. This is correct. The frequency of the wow signal alone does not prove its origin. It is one piece of evidence among many, and like all the pieces, it is suggestive rather than conclusive. It fits the profile. It matches the prediction. But fitting a profile is not the same as being identified. The narrowband nature of the signal is, for many researchers, its most provocative characteristic. It is very difficult to explain by natural processes. Hydrogen emission from interstellar clouds can look narrowband under some circumstances, but the intensity of the wow signal and its precise frequency profile make a natural hydrogen cloud origin very difficult to account for. And so we return to the hydrogen line, to this elegant, universal frequency, this meeting point of physics and possibility, this watering hole in the radio spectrum. The wow signal arrived here, of all places. It arrived at exactly the frequency that the theorists had predicted. It arrived with precisely the shape and duration expected from a point source at astronomical distance. And then it went quiet. The universe, it seems, knows how to be mysterious. It left us a clue that fits every criterion we asked for, and then provided no further information. It handed us a single piece of a puzzle with no other pieces and no picture on the box. Part 5, The Sky Above, Where Did It Come From? What lies in that patch of sky from which the signal arrived? Every radio signal comes from somewhere. Even if we cannot identify its source, we can point to the place in the sky from which it arrived. And the coordinates of the wow signal's origin are known, at least approximately. The uncertainty is not enormous, but it exists, and it matters. The signal appeared to come from the direction of the constellation Sagittarius. More precisely, it came from one of two possible locations near the constellation's boundary. The uncertainty arises from the fact that Big Ear had 2 feed horns, and researchers cannot determine with complete certainty which horn detected the signal, which gives 2 possible source positions about 3 degrees apart on the sky. Sagittarius is a constellation of the southern sky, rich in stars and deep sky objects. When you look toward Sagittarius, you are looking toward the center of our galaxy, the direction of the Milky Way's bulge, where stars are most densely packed and the ancient heart of our galaxy resides. It is one of the most rewarding regions of the sky for a telescope of any kind, filled with star clusters and nebulae and the faint traces of a galaxy's long history. In the specific region of Sagittarius where the wow signal apparently originated, there are no known stars that stand out as obvious candidates for the source. Neither of the 2 possible source positions corresponds to a nearby sun-like star of the kind that SETI researchers tend to prioritize. The region has been studied extensively in the decades since the signal was detected, and no obviously compelling candidate has been identified. This does not rule out a distant source. The signal could have originated from a star hundreds or thousands of light-years away, beyond the easy reach of detailed study. The universe does not organize itself for our convenience. An intelligent signal could come from a civilization far enough away that we would not easily identify their star in a catalog, particularly given the modest angular resolution of Big Ear and the limited supporting observations that were made at the time. In 2017, a group of researchers announced that they had analyzed archival data from the All-Sky Automated Survey (ASOS) and identified a pair of stars, known as 2mas19281982-2640123 and 2mas19841995-2647126, that lie in one of the two possible directions of the WOW signal. These are sun-like stars, of a type that SETI researchers consider promising candidates for harboring habitable planets. The researchers, led by Antonio Paris of St. Petersburg College in Florida, suggested that these stars might be a natural explanation for the signal, not as sources of intelligent transmission, but as hosts for cometary activity that could produce radio emission resembling the WOW profile. The cometary hypothesis was an interesting proposal. The idea was that comets, as they approach a star and their icy surfaces are heated by starlight, release gases including hydrogen. A comet in the right orbit around one of these sun-like stars might produce a cloud of hydrogen dense enough to emit radio waves at the hydrogen frequency, creating a narrowband signal that could, under some circumstances, resemble the WOW signal's profile. The hypothesis received some attention, but also significant criticism from researchers who had studied the WOW signal carefully. The most vocal critic was Jerry Emin himself, who noted that for a comet to produce a signal matching the WOW profile, it would need to be stationary relative to the background stars, which comets are not. Comets move across the sky. A cometary source would have produced a signal that drifted in frequency or disappeared from the telescope's beam more quickly or more slowly than the WOW signal did. The precise 72-second bell curve profile of the signal is inconsistent with a moving source like a comet. Other researchers pointed out that no comets were known to be in the right area of the sky in August 1977. The Paris hypothesis required assuming the presence of uncharted comets, which made the explanation somewhat ad hoc. A hypothesis that requires the invention of unknown objects to explain a phenomenon is always less satisfying than one that can invoke known, confirmed entities. And so the cometary hypothesis, while interesting, did not resolve the mystery. It added another candidate to the list of possible explanations but failed to achieve the explanatory elegance that would settle the question. The question of source location matters enormously to the interpretation of the signal. If the source were a nearby sun-like star, it would strengthen the case for an intelligent origin, though it still would not prove it. If the source were a known natural object with known properties, it might provide a natural explanation. If the source is truly nothing identifiable in that patch of sky, then we are left with the same open question we started with. Perhaps the most profound aspect of the source question is this: the universe is 13.8 billion years old. The patch of sky from which the WOW signal came has been in existence for all of that time. Whatever produced the signal, a civilization or a natural process, has had billions of years to develop. If it was a civilization, it may be ancient beyond our imagination, may have begun its story when our sun had not yet condensed from gas and dust. When we point our telescopes at that corner of Sagittarius, we are looking at something that is, at minimum, many hundreds of light years away. The signal we detected in 1977 traveled for hundreds or perhaps thousands of years to reach our planet. Whatever world it originated from, whatever sun warmed it, that world was sending radio waves into space when our ancestors walked in medieval cities, or perhaps long before that. That distance, that age, is part of what gives the WOW signal its peculiar weight. It is not simply a radio blip. It is a potential message in a bottle from across an ocean of time, delivered to our shores after a journey that dwarfs all of recorded history. The question of where this signal came from remains open. The sky holds that corner of Sagittarius in its arms, and it gives no further clues. We can only look, and measure, and think. Part 6. The silence after years of searching and finding nothing. What does it mean to search for something and find only absence? After the discovery of the WOW signal, the Ohio SETI program and the broader scientific community entered what might be called the Age of Silence. Not a literal silence, the telescopes kept listening, the data kept coming. But the remarkable signal of August 15, 1977, did not repeat. Did not echo. Did not follow up. In the immediate aftermath of Emmons' discovery, the team at Big Ear was understandably energized. They devoted their most sensitive observations to the region of sky from which the signal had come. They pointed the telescope at those coordinates every time Earth's rotation brought them into view. They listened with particular care, with all the attention they could muster. Nothing came. The Great Arecibo Telescope, the enormous 300-meter dish in Puerto Rico, the most powerful radio telescope on Earth at the time, was also directed at the source coordinates. The sensitivity of Arecibo was far greater than that of Big Ear. If the signal had a repeating component, if it was broadcasting continuously, Arecibo should have been able to pick it up. Arecibo heard nothing. Other observatories around the world conducted their own follow-up observations. Different frequencies were checked. Different times were monitored. Different equipment was brought to bear on the problem. All of it resulted in the same silence. Over the decades that followed, the WOW signal remained an isolated datum, a single point of extraordinary significance surrounded on all sides by ordinary noise. Researchers developed increasingly sensitive instruments, broader frequency coverage, more sophisticated signal processing techniques. The modern SETI search, conducted by organizations like the SETI Institute in California, has capabilities that dwarf what was available at Big Ear in 1977. And still, no confirmed repeat of the WOW signal has been found. This silence is one of the most confounding aspects of the mystery. If the signal was produced by a civilization broadcasting continuously, a cosmic lighthouse, sending its beam out into the darkness in hopes of being found, then repeated observations should have detected it again. The fact that it has not been redetected is troubling for the intelligence hypothesis. But there are reasons why a non-repeating signal might not necessarily rule out an intelligent origin. Consider the geometry of the problem. Big Ear was not a steerable telescope. It scanned the sky in a fixed pattern, observing each point for only 72 seconds per day. If the source was broadcasting intermittently, in regular pulses separated by hours, days, or years, the telescope might easily miss subsequent transmissions simply because they happened to fall outside its brief daily window of observation. Or consider the possibility of a directional beam. A civilization conserving energy might not broadcast in all directions simultaneously but might instead sweep a narrow beam across space, reaching different planetary systems at different times. Like a lighthouse sweeping its beam around a harbor, the signal might have been directed toward our solar system only briefly, by chance or by design, and might have moved on. Or the civilization might have been transmitting only once, deliberately sending a single message, or triggering a one-time beacon, for reasons we cannot guess. A civilization that has been broadcasting for millions of years might have long since given up and decided to send only a single pulse per stellar system that came into range. All of these are speculative possibilities, none of them verifiable. What is verifiable is the silence itself. The absence of recurrence. The long years of listening that produced nothing to compare with those few seconds in August 1977. There is a particular kind of loneliness in this search. The astronomers and engineers who devoted years of their lives to listening to the sky, who gave evenings and weekends and decades to the project of waiting for a signal, did so without any guarantee of success, with only the cold arithmetic of probability to sustain them. Most of them heard nothing they could not explain. Most of them went their entire careers without a wow moment. And even Emin, who had his moment, could not be certain of what he had found. The signal was real. The data were clear. But what it meant, where it came from, what produced it, remained elusive. He had the printout. He had the red circle and the handwritten word. And he had 40 years of silence in which to wonder. The silence after the wow signal is not just an absence of data. It is an argument that requires careful handling. The universe is under no obligation to repeat itself for our convenience. A signal that arrives once and never again is still a signal. An event that occurs once in the history of science is still an event. The fact that something has not been confirmed does not mean it did not happen. And yet, and this is the honest, necessary tension at the heart of the story, the absence of repetition is real evidence. It is not nothing. In science, negative results matter. They constrain the possibilities. They narrow the field. The long silence after the wow signal tells us something, even if what it tells us is not yet clear. Perhaps it tells us that the signal was not a continuous broadcast. Perhaps that the source has since gone dark. Perhaps that the signal was never intelligent at all, but a natural phenomenon so rare that it has simply not recurred in the decades since. Perhaps that our search methods are still too limited to catch a non-repeating signal in the act of repeating, that we need more telescopes, more sensitivity, more coverage. The silence is a clue. It is not yet a solution. Part 7. What could it have been? The natural explanations. Is there a simpler answer hidden in the physics? Science is, at its most fundamental level, the art of finding the simplest explanation that accounts for the observed facts. Before we embrace the remarkable, we must exhaust the ordinary. Before we reach for the extraordinary explanation, we must be quite sure that no ordinary one will do. And so it is with the wow signal. In the decades since its discovery, researchers have proposed a variety of natural, non-intelligent explanations for what Big Ear detected that August. Each of these explanations has merits and limitations. None of them has been definitively confirmed as the solution. And taken together, they represent the scientific community's honest attempt to think carefully before concluding that something unprecedented has occurred. The first category of natural explanation involves terrestrial radio frequency interference, or RFI. This is the most mundane possibility. The signal was not from space at all, but was produced by some human-made source of radio emission that found its way into Big Ear's antenna system. Radar installations, communications satellites, aircraft, television, and radio broadcasts, all of these can produce radio signals at frequencies near the hydrogen line, and all of them have been cited at various times as potential sources of RFI. Nevertheless, the possibility of RFI cannot be entirely ruled out. We do not have a complete catalog of every radio transmission that might have been active in the vicinity of Big Ear on the evening of August 15, 1977. Military radar systems, in particular, are not always documented in publicly available records, and their operating parameters are sometimes classified. The second category of natural explanation is astrophysical. Perhaps the signal was produced by some unusual natural object, a pulsar, a magnetar, an interstellar maser, a distant galaxy undergoing some violent event, that produced a brief, intense, narrowband radio emission at the hydrogen frequency. Pulsars are rapidly rotating neutron stars that emit beams of radio radiation. As they spin, these beams sweep through space like cosmic lighthouse beams, producing brief, regular pulses detectable at radio wavelengths. Some pulsars emit at frequencies near the hydrogen line. Could the WOW signal have been produced by a pulsar? The difficulty here is that pulsars pulse regularly. Their timing is extraordinarily precise. Pulsars are among the most accurate natural clocks known to science. A pulsar that produced the WOW signal in 1977 should still be pulsing today, at the same frequency, with the same precision. But no pulsar has been found at the relevant sky coordinates, and subsequent observations have detected no such regular pulses. Magnetars are a type of neutron star with extraordinarily strong magnetic fields. They occasionally release enormous bursts of energy, including radio bursts. Fast radio bursts, brief, intense pulses of radio emission detected from distant galaxies, have become a major area of astrophysical research in recent decades, and some of them have properties that superficially resemble the WOW signal. Could the WOW signal have been an early, unrecognized fast radio burst? Interstellar masers, regions of gas in which radio emission is amplified by stimulated emission, the same physical process that creates a laser beam but operating at radio wavelengths, can produce intense, relatively narrowband radio emission at specific frequencies. Hydroxyl masers, for example, are common astronomical objects. But hydrogen masers at 21 centimeters are less common, and the intensity of the WOW signal, combined with its precise profile, makes a maser origin difficult to sustain without additional supporting evidence. There is also the cometary hypothesis we mentioned earlier. A comet outgassing hydrogen could theoretically produce radio emission at the hydrogen line. But as we discussed, the non-moving, stationary source profile of the WOW signal is inconsistent with a comet, which would be in motion relative to the background stars and would produce a signal that drifted in frequency or changed its apparent position. Each of these natural explanations has been examined by researchers who understand radio astronomy deeply. Each has been found wanting in one way or another, not necessarily impossible, but not convincingly demonstrated either. The WOW signal sits between the confirmed and the explained, in the space where evidence is real but interpretation remains genuinely open. There is something important to recognize in this. The fact that natural explanations have not been confirmed is not the same as saying that the signal must be artificial. Science proceeds by elimination, but elimination requires positive evidence for an alternative. We cannot prove the signal was intelligent simply because we cannot prove it was natural. The honest position is that we have not yet found an explanation, of any kind, that fully accounts for all the characteristics of the signal. And in science, an unexplained observation is not a failure. It is an invitation. It is the universe extending its hand and saying, "There is something here you have not yet understood. Come closer." Part 8. The Drake Equation and the Weight of Silence. What does mathematics have to say about loneliness? When Frank Drake organized the first SETI meeting in Green Bank in 1961, he devised an equation. He wrote it on a blackboard before the meeting began, as a way of organizing the group's discussion. He had not planned to publish it or to give it a name. He simply wanted a framework. The equation became famous. It is known as the Drake equation, and it attempts to estimate the number of detectable civilizations in the Milky Way galaxy at any given time. It does this by multiplying together a series of factors: the rate at which stars form in our galaxy, the fraction of those stars that have planets, the fraction of those planets where life might arise, the fraction of those life-bearing planets where intelligent life evolves, the fraction of those civilizations that develop technology and transmit detectable signals, and the average length of time that such civilizations continue transmitting. The equation is not a prediction. It is a framework for organizing our ignorance. For most of its variables, we simply do not know the values. We have made progress on some of them. We now know, from missions like Kepler and TESS, that planets around other stars are common, perhaps averaging more than one per star in the galaxy. We have some sense of how often sun-like stars form. But the crucial biological and social variables, how often life arises, how often it becomes intelligent, how long technological civilizations last, remain deeply uncertain. The physicist Enrico Fermi, at a lunch conversation at Los Alamos in 1950, posed what has become known as the Fermi paradox. The argument is simple: if the universe is old enough and large enough for millions of civilizations to have arisen and developed technology over billions of years, then some of them should have had time to colonize the entire galaxy, or at the very least to fill it with detectably artificial signals. The galaxy is billions of years old. Even traveling at a small fraction of the speed of light, a civilization with enough determination and time could populate the entire Milky Way in a few tens of millions of years, a blink in cosmic time. But we see no signs of this. Our instruments have not detected obvious, unmistakable evidence of widespread galactic civilization. The stars are not surrounded by obvious artificial megastructures. The radio spectrum is not filled with the communications of 1,000 civilizations. The sky is, as best we can tell, quiet. "Where is everybody?" Fermi asked. It was a lunch table joke, not a formal argument. But the question has haunted SETI ever since, and the wow signal sits in the middle of it like an island in a still sea. Some researchers have proposed what they call the Great Filter, the idea that somewhere in the sequence of steps from simple chemistry to starfaring civilization, there is an obstacle so severe that almost no species makes it through. The filter might be behind us, perhaps the development of the eukaryotic cell, or multicellular life, or intelligence itself is so unlikely that it has occurred only once or a handful of times in the entire galaxy. Or the filter might be ahead of us, Perhaps civilizations tend to destroy themselves with weapons or ecological collapse before they become truly widespread. The wow signal does not resolve this question. If it was intelligent, it suggests that at least one other civilization has reached the radio technology stage. But one confirmed signal from one civilization does not tell us whether that civilization still exists, whether others exist, or whether the filter is behind us or ahead. There is a particular melancholy in the Drake equation when you sit with it quietly. It is an equation that asks how alone we are, and it cannot answer. It holds its variables loosely, uncertain and yielding, and offers no final sum. You can plug in optimistic numbers and find a galaxy buzzing with life. You can plug in pessimistic numbers and find yourself alone in a universe so large that loneliness is not even a meaningful concept. And in between those extremes, there sits the wow signal, one data point, one moment, one printout with a red circle around it. A single possible message from somewhere in the dark. Whether it resolves the Drake equation or merely decorates it, we cannot say. What we can say is that it changed the way many scientists thought about the search. Before the wow signal, SETI was entirely theoretical, a search with no positive results of any kind, sustained only by logic and hope. After the wow signal, there was at least the possibility of success. The telescope had caught something. Something that didn't fit the expected noise. Something that bore the hallmarks of the signal that the theorists had predicted. Even if it was never explained, never confirmed, never repeated, it had happened. The universe had, for 72 seconds, produced something that made a man pick up a red pen and write a single word. And that word still means something. Even after all these years. Part 9, the Arecibo message, we tried to answer. If someone called out in the dark, what would you say back? 3 years before the wow signal arrived, humanity had already tried to make itself heard. In November of 1974, the Great Radio Telescope at Arecibo, Puerto Rico, was used to transmit a message into space. The message was directed at the globular star cluster Messier 13, a dense swarm of approximately 300,000 stars located about 25,000 light-years from Earth. The Arecibo message was designed by Frank Drake and his colleagues, with input from a young and brilliant scientist named Carl Sagan, who would go on to become the most famous science communicator of his era. The message was a sequence of 1,679 binary digits, ones and zeros, that, when arranged into a 73 by 23 grid, formed a pixelated image containing information about the building blocks of chemistry, the structure of DNA, a depiction of a human figure, a representation of our solar system, and a diagram of the Arecibo telescope itself. The number 1679 was chosen deliberately. It is the product of two prime numbers, 23 and 73. Any civilization with sufficient mathematical sophistication to receive and decode a binary message would likely recognize that a sequence of this length could be arranged into a rectangle with prime number dimensions, and would try both arrangements. Only the 73 by 23 arrangement produces a coherent image. The 23 by 73 arrangement is just noise. The message will take approximately 25,000 years to arrive at its destination. If anyone there receives it and replies, the reply will take another 25,000 years to reach us. The Arecibo message is, in practical terms, not a communication but a gesture. A statement that we exist. A proof that we are here, that we think, that we use mathematics and chemistry and build structures that focus radio waves. Sagan was a man of profound scientific discipline and equally profound humanistic imagination. He understood that the search for extraterrestrial intelligence was not just a scientific endeavor but a philosophical one. It was a way of asking who we are by asking who else might be out there. It was a way of confronting our place in the cosmos, our smallness and our remarkable improbability. He would later write about what it would mean to detect a signal from another civilization, even a signal we could not fully understand. Merely knowing that we are not alone, he argued, would transform our self-conception as a species. Our tribal divisions, our conflicts, our sense of cosmic insignificance, all of it would be reframed by the knowledge that intelligence had arisen elsewhere, that consciousness was not a unique accident of one small world. When the WOW signal was detected 3 years after the Arecibo transmission, Sagan was among those who took it seriously. He was cautious, he was always cautious, because caution is what science requires, but he was also genuinely moved by the possibility that the signal represented. He wrote about it. He thought about it. He returned to it throughout his career as a touchstone, a reminder of what the search was for. In 1985, Sagan published his novel Contact, in which a radio astronomer detects an artificial signal from the star Vega. The novel draws deeply on Sagan's experience with SETI, on the WOW signal and the culture of the search, on the human reality of what it would feel like to find something. The book, and the film adapted from it in 1997, brought the ideas of Radio SETI to millions of people who had never heard of Frank Drake or Jerry Emmon or Big Ear. Sagan died in December of 1996, just months before the film of Contact was released. He had spent much of his life thinking about whether we were alone. He never found out. None of us have, yet. But his work, the novels, the essays, the television series, the tireless advocacy for the scientific search, did something essential. It kept the question alive in the public mind, maintained the sense that the question was worth asking, that the search was worth funding. The Arecibo message and the WOW signal sit in a particular relationship to each other across the decades. One was humanity reaching out. The other was, perhaps, something reaching back. Or perhaps not. Perhaps both were simply coincidences of physics and timing, human transmitters and human receivers finding nothing but their own echo in the dark. But the relationship between them, the fact that within 3 years of our first serious attempt to say hello to the cosmos, we caught something that might have been a hello in return, is one of those coincidences that makes the mind pause. That makes you wonder, in the soft space between sleeping and waking, whether the universe is listening as carefully as we are. Part 10, The Science That Came After, How the Search Evolved. What did the WOW signal teach us about how to look? A mystery, even one that remains unsolved, can be a powerful engine of progress. The WOW signal did not just sit in a filing cabinet growing dusty. It inspired new thinking, new technology, new approaches to the problem of searching for signals from space. In a very real sense, the signal that was never explained helped define the science that came after it. In the years following the WOW Discovery, SETI research expanded and diversified significantly. The signal had demonstrated that something unexpected could appear in the data, that the patient, methodical work of scanning the sky was not necessarily futile. Even if the source of the WOW signal remained uncertain, the fact of its detection strengthened the argument that the search was scientifically worthwhile. The Surrender program at the University of California, Berkeley developed a different approach, piggybacking on existing telescope observations. Rather than dedicating telescope time exclusively to SETI, Surrender attached signal processing equipment to radio telescopes that were being used for conventional astronomy, analyzing the radio data in real time for any anomalies. This allowed the SETI search to proceed more or less continuously without competing for limited telescope time. The Surrender approach led, in 1999, to the launch of SETI at Home, one of the most innovative scientific computing projects ever undertaken. The idea was elegantly simple. The enormous volumes of data produced by Surrender observations were too large for a single computer to process in real time. But if the data could be distributed to millions of personal computers around the world, each processing a small piece of the puzzle during their idle time, the aggregate computing power would be immense. SETI at Home invited members of the public to download a screensaver that would analyze radio telescope data in the background while their computers were not in use. At its peak, millions of volunteers were participating, contributing their personal computers to the collective search. It was one of the first major examples of distributed computing applied to a real scientific problem, and it proved the concept in ways that influenced computing culture for decades. SETI at Home processed more than a petabyte of data over its 20-year history. It detected more than 1 billion signals worth investigating. But it found no confirmed evidence of extraterrestrial intelligence. The project was placed in hibernation in 2020, not because it had failed, but because the team had more data than they could analyze even with all that computing power, and they needed time to develop better algorithms. FAST has been used for SETI observations, scanning thousands of stars and monitoring the radio sky with unprecedented sensitivity. It has detected fast radio bursts and studied pulsars. It has not, so far, found a signal resembling the WOW observation. In 2015, a new initiative called Breakthrough Listen was announced by the billionaire entrepreneur Yuri Milner and scientific advisory board that included Stephen Hawking. With funding of $100 million over 10 years, Breakthrough Listen represented the largest private investment in SETI in history. It secured dedicated time on major radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, and began a systematic, comprehensive survey of the 1 million nearest stars and the 100 nearest galaxies. But the program continues. The telescopes are still listening. The data is still being analyzed. And the WOW signal still hangs in the literature as the one unexplained case, the one observation that has not been satisfactorily assigned to a known source, the benchmark against which all future candidates must be compared. There is a deeper lesson in the evolution of SETI technology after the WOW signal, and it is a lesson about the nature of scientific progress. The signal did not provide an answer, but it provided a question with sufficient specificity that it could drive the development of better tools. We now know what a strong, unexplained, narrowband signal at the hydrogen frequency looks like. We have a template, imperfect, single, contested, but real. And we have built instruments and programs specifically designed to find more like it. Whether those instruments will succeed, whether the universe will again produce something that compels a scientist to reach for a red pen, we do not know. But the architecture of the search has been built, in part, around that 172-second event in the summer of 1977. The wow signal shaped the science that followed it. It was not just a mystery. It was a teacher. And teachers sometimes give lessons whose meaning only becomes clear much later, when the student has had time to grow into the question. Part 11, The Human Story, Lives Given to Listening. What does it cost a life, to give it to a question that may not be answerable? There is a human dimension to this story that the data and the science cannot capture on their own. The wow signal is not just a datum. It is the product of years of work by real people, scientists and engineers who built instruments, wrote code, reviewed printouts, and spent careers asking a question that most of their colleagues considered eccentric at best and foolish at worst. John Krauss, who designed Big Ear, was a man of extraordinary breadth. He was a radio engineer whose textbooks on antenna design and electromagnetics were standard references for generations of engineers. He had served in the Navy during the Second World War, working on radar technology, before returning to academia and eventually combining his engineering expertise with his love of astronomy. He spent decades at Ohio State, building and operating Big Ear, supervising the SETI program with a quiet dedication that was characteristic of his personality. Krauss understood that the search for extraterrestrial intelligence was a long-term project. He was under no illusion that Big Ear would necessarily succeed in his lifetime. He saw his work as a contribution to an effort that might take generations, a relay race in which each scientist carries the baton forward a little further before passing it on. He was patient with the search in the way that people who truly understand the scale of the universe must be patient. A universe billions of years old rewards patience. Robert Dixon was another key figure in the Ohio SETI program, the director of the project during much of its most productive period. Dixon was a computer scientist and astronomer who developed much of the data analysis software that made the program possible. He believed deeply in the value of systematic, methodical observation, the conviction that if you listen long enough and carefully enough, the universe will eventually say something surprising. Dixon was instrumental in preserving the legacy of Big Ear after the telescope was demolished in 1997. He worked to ensure that the data was archived and made available to researchers, and he continued to advocate for the analysis of the existing dataset in hopes that new analytical techniques might reveal something that had been missed. Jerry Emin, the man who found the signal, lived with the weight of his discovery for decades. He remained associated with the Ohio SETI program and continued to analyze and defend the data long after the initial excitement had faded. He was a careful and rigorous thinker who consistently resisted the temptation to overclaim. In interview after interview, across many years, he would explain what the signal was, what it was not, and what it might or might not mean. He never said it was extraterrestrial. He never said it was not. He held the uncertainty with a kind of professional dignity that is genuinely admirable. Emin once said, in a particularly thoughtful interview, that if he had to guess, he would say the signal was most likely produced by a natural astronomical source, something we simply have not yet identified. But he also said that he could not rule out an artificial origin. The data, he maintained, was consistent with both possibilities. The data alone could not decide. This intellectual honesty is worth dwelling on. In a culture that often rewards certainty over accuracy, Emin's refusal to commit beyond what the evidence supported was a form of courage. It would have been easy, and financially and reputationally rewarding, in some circles, to proclaim that he had detected alien intelligence. It would have been equally easy to dismiss the observation as obvious interference and move on. He did neither. He sat with the uncertainty and did his best to characterize it precisely. There were others, less well known outside the SETI community, who contributed years of their lives to the search. Volunteers who processed printouts, engineers who maintained the equipment, graduate students who wrote their theses on signal processing algorithms, professors who defended the value of the search to skeptical funding committees. The history of SETI is populated not just by famous names but by a long procession of ordinary scientific workers who believed that the question was worth asking. And there were the critics. SETI has always had critics, serious scientists who argued that the search was methodologically flawed, that it rested on assumptions too uncertain to sustain a research program, that the resources devoted to it would be better spent on more tractable scientific problems. These critics were not wrong to raise their concerns. Science requires skepticism, including self-skepticism. The value of SETI as a scientific enterprise has been legitimately debated for decades. But the critics, for all their reasonable concerns, faced a simple counter-argument. If the question of whether we are alone in the universe is among the most important questions a conscious species can ask, then it is worth some investment in the search for an answer, even if that answer is not guaranteed. And if the answer turns out to be yes, if the universe is populated with other minds, other cultures, other histories, then no amount of money or time spent on this search could be considered wasted. The human story of SETI is also a story about institutional support and its absence. For much of its history, the search received very little public funding. NASA funded a brief but ambitious program called the High Resolution Microwave Survey in the early 1990s, which was canceled by Congress after just 1 year with a dismissive comment from a senator who saw it as a search for little green men. The SETI Institute, founded in 1984, has relied primarily on private funding, from technology entrepreneurs, from foundations, from individual donors who believe the question matters. This financial precariousness has shaped the search. It has meant working with whatever telescope time can be arranged, developing clever approaches that don't require dedicated facilities, making do with limited resources. In a way, this adversity has been productive. It has forced SETI researchers to be creative, to develop the distributed computing approaches of SETI at home, to find ways of piggybacking on existing infrastructure. But it has also meant that the most capable instruments on Earth have only occasionally been pointed at the sky with the specific purpose of listening for intelligence. The amount of time that humanity has actually, seriously, with full scientific attention, listened for signals from space is remarkably small compared to the vastness of what needs to be searched. We have scanned only a tiny fraction of the stars in our galaxy, at a limited range of frequencies, for a limited period of time. The universe, if it is trying to be heard, is not making it easy. But perhaps that is appropriate. Perhaps the most important discoveries require exactly this, the quiet persistence of people who show up, who look at the data, who circle things in red and write their honest reactions in the margins. The human story of the wow. Signal is a story about patience and humility. About the willingness to ask a question that may not be answerable in your lifetime. About the courage to report something remarkable without claiming more than the evidence supports. About the dignity of sitting with uncertainty and continuing to listen. These are not small things. In a world that moves faster every year and demands quick answers to complex questions, the scientists who listened to the sky with big ear for 22 years were practicing something rare and valuable. They were demonstrating that some questions are worth the wait, whatever the wait may cost. Part 12, The Ongoing Mystery, What We Still Don't Know and Why It Matters. What does it mean to live in a universe that may have spoken once and then gone silent? After everything, after all the analysis, all the follow-up observations, all the competing hypotheses, all the decades of silence, the wow signal remains exactly what it was on the day Jerry Emmons circled it in red pen. It is a mystery. A genuine, unresolved, scientifically respectable mystery that sits at the intersection of physics and philosophy, astronomy, and the deepest questions of human existence. Let us take stock of what we know and what we do not know, with the same honesty that the scientists who have studied this signal have tried to maintain. We know that a real radio signal was detected by Big Ear on August 15, 1977. The data is not in dispute. The signal is recorded on paper, analyzed by multiple researchers, published in scientific literature. It happened. Whatever it was real. We know that the signal lasted approximately 72 seconds, the exact duration expected from a point source at fixed astronomical coordinates passing through Big Ear's field of view as the Earth rotated. This is consistent with an origin at an astronomical distance. We know that the signal appeared at a frequency very close to the hydrogen line, in a region of the radio spectrum where we would expect an intelligent transmitter to broadcast if it wanted to be found, and where many natural astrophysical sources also emit. We know that the signal was narrowband, confined to a very small range of frequencies, in a way that is more characteristic of an artificial transmitter than of most known natural sources of radio emission. We know that the signal appeared in only one of Big Ear's 2 feed horns, which is unexplained but not necessarily conclusive. We know that the signal has never been detected again, despite repeated and sensitive observations of the source coordinates by multiple instruments. We do not know what produced the signal. We have not identified a natural astrophysical object at the relevant coordinates that could account for its characteristics. We have not confirmed any terrestrial interference source that could mimic its profile. We have not identified any candidate transmitting civilization. We do not know whether the signal was produced by an intelligent source or a natural one. Both possibilities remain consistent with the data. We do not know why it has not repeated. If it was an artificial signal, the transmitter may have turned off, or changed direction, or been destroyed. If it was a natural phenomenon, the conditions that produced it may not have recurred. We do not know if we will ever know. This last point is the most philosophically interesting one. There is a real possibility that the wow signal will remain permanently unexplained, not because science fails to investigate it, but because a single, non-repeating observation from almost 50 years ago, with limited instrumentation, may simply not provide enough information to determine its origin. We may have reached the boundary of what the evidence can tell us. If that is the case, then the wow signal becomes something more than a scientific datum. It becomes a parable. A story about the limits of knowledge and the nature of wonder. A reminder that the universe does not owe us explanations, that mysteries can persist not because we are insufficiently clever but because information is finite and the cosmos is vast. But the story is not necessarily closed. Science continues to advance. Our instruments grow more sensitive, our analytical methods more sophisticated, our catalog of the sky more complete. There are things we can do now that were impossible in 1977, and things that will be possible in 2050 that we cannot yet imagine. The Square Kilometre Array, SKA, is a radio telescope currently under construction in South Africa and Australia, which when complete will be the largest and most sensitive radio telescope in history, with a collecting area totaling 1 square kilometre. The SKA will be able to detect radio signals at distances and sensitivities that completely dwarf anything previously possible. It will open the radio sky to an entirely new depth of investigation. If the source of the WOW signal exists and continues to transmit, the SKA might find it. If it was a natural phenomenon that occasionally recurs, the SKA might catch it in the act. If it was a one-time event, the SKA might at least tell us what it was not, by systematically ruling out candidate sources and phenomena. There is also the possibility of entirely new approaches that we have not yet conceived. The history of astronomy is full of discoveries that came not from looking harder in already known directions, but from opening a new window, a new wavelength, a new detection method, a new way of processing information. Gravitational wave astronomy, which began with the detection of merging black holes in 2015, revealed an entirely new way of observing the universe. Neutrino astronomy is still developing. The future may hold detection methods that we currently cannot anticipate. Perhaps the signal we have been calling the WOW signal will one day be recognized as the first faint note of a communication that future generations will eventually decipher. Perhaps it will be identified as a rare but natural phenomenon, catalogued alongside other curious astrophysical objects. Perhaps it will remain forever in the category of things that happened and were never fully explained, the Tunguska event of radio astronomy, a real observation with a contested origin. Any of these outcomes would be interesting. All of them are consistent with the evidence. The universe is large enough to contain all of them simultaneously, in the sense that it contains multitudes of phenomena we have not yet understood. But perhaps the most important thing the WOW signal teaches us is something about the relationship between searching and finding. We sometimes imagine that the purpose of a search is to find the thing we are looking for. But there is another purpose that may be equally valuable: the search itself changes us. The act of listening changes the listener. The people who built Big Ear, who pointed it at the sky, who reviewed the data, who spent careers asking whether we are alone, they were changed by the question. Carl Sagan was changed by it. The millions of people who downloaded the SETI at home screensaver and contributed their computers to the search were, in some small way, changed by it. The question of whether we are alone is not a question with a neutral relationship to those who ask it. It reorganizes priorities. It enlarges perspective. It makes the immediate and the local feel smaller, and the vast and the ancient feel more real. When you lie in the dark tonight, as you drift toward sleep, you are lying on the surface of a planet that is rotating slowly on its axis, as it orbits around a star that is moving around the center of a galaxy that is moving through an expanding universe. You are listening to silence. But the sky above you is not truly silent. It is full of radio waves, from stars and galaxies and pulsars and the cosmic background and, possibly, from transmitters built by minds we have never met. In 1977, for 72 seconds, something in that radio sky was briefly, inexplicably brighter than everything else. It caught the attention of a patient instrument and a curious mind. It was circled and read and given a name. And then it faded, and the sky went back to its ordinary murmur, and the question it raised, if it raised a question at all, was left hanging. It is still hanging now. The universe is still out there, filling the sky above you with its ancient radio whisper. The hydrogen atoms in the interstellar gas are still flipping their tiny magnetic fields and releasing their tiny packets of energy at 1420 MHz, as they have been doing since before our sun existed. If there is another civilization somewhere in that vast dark, they may be listening to that same frequency, hearing the same background hiss, wondering the same things we wonder. Or they may have given up listening and be doing something else entirely, something that has nothing to do with radio waves, something we cannot imagine. Or they may not exist at all. We do not know. We have not yet found out. What we have found out is that the search is worth conducting. That the universe is large enough and old enough and strange enough that it is reasonable to expect it to contain more than we have so far discovered. That a single printout from an August night in Ohio, with a red circle and a single word in the margin, can sustain nearly 50 years of scientific inquiry and philosophical reflection. That sometimes the most important thing that happens is not the finding but the wondering. Not the answer but the question, held carefully, turned over in the hands of curious people, examined from every angle, never discarded. The wow signal is a question. It has been asked. It has not been answered. And perhaps that is exactly as it should be, for now. The universe has not finished revealing itself. We have not finished listening. The story is not over. In fact, tonight, somewhere on the Earth, a radio telescope is pointed at the sky. Its receivers are tuned to frequencies near the hydrogen line. Its computers are recording data. A scientist somewhere is looking at numbers, or an algorithm is running, or a volunteer's computer is processing a small packet of information in the background while its owner sleeps. They are listening. The sky is breathing its quiet electromagnetic breath. And somewhere in that cosmic radio ocean, something may be waiting to be heard. We just have to keep listening. Closing meditation. You have traveled far tonight. Not in miles, but in something else, in the deep, quiet geography of wonder. You have heard about a signal that arrived on a summer day in Ohio and left a single mark on a piece of paper. You have heard about the people who built the instruments and reviewed the data and gave their patient attention to the sky. You have heard about hydrogen atoms flipping their electron spins in the dark between the stars, and about the silence that followed the most intriguing detection in the history of radio astronomy. None of it has been resolved tonight. The universe does not offer those kinds of resolutions on a schedule. The mystery is still out there, hanging in the sky above you, mixed in with the hydrogen and the ancient starlight and the long whisper of the cosmos going about its enormous business. And that is all right. It is more than all right. A mystery held with care is one of the finest companions a curious mind can have. It does not demand anything from you tonight. It asks only that you remain open to the question, that you carry it lightly, the way you carry the memory of a beautiful dream after waking. You are lying on a spinning world. Above you, through the ceiling and the roof and the atmosphere and the vast nothing of space, there are hundreds of billions of stars in this galaxy alone. Radio waves are passing through you right now, signals from pulsars and distant galaxies, and the faint echo of the Big Bang itself. You are immersed in the universe at all times. It is not distant. It is here. Let your breathing slow now. Let the questions dissolve into the gentle darkness of sleep. You do not need to hold on to any of this. It will be there when you wake, the hydrogen line, the red circle, the summer night in Ohio, the 72 seconds that changed how we think about the sky. Let your body rest. Let your mind drift into the warm dark space between the questions and the answers, that vast and comfortable place where the universe does its best and most mysterious work. The telescopes are still listening. The sky is still there. And somewhere, in some direction we could roughly point to, the source of the wow. Signal may still exist, a star, a world, a civilization, a natural phenomenon, something. Still out there. Still part of the same universe that holds you now, gently, as you sleep. Good night. Sleep well. The stars will keep watch. If you're still awake, the universe is vast and full of wonder. Subscribe to Cosmos and Dreams for a new discovery every week. Sweet dreams.